So after playing with that applet, I hope that you, by looking at smaller and smaller values of h, that is, as h was getting closer and closer to 0, you did conclude that based on the numerical evidence that this limit does exist, and in fact that it equaled some number 0.693 something 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 something. It didn't seem like as h was going to 0, this limit was bouncing around or going to infinity or going to negative infinity or anything funny like that. It did seem like it was settling down at this particular number. So at least we think that this derivative exists, which is no surprise. Based on the graph of 2 to the x, we should be able to find a slope at any given x value. We could do exactly the same work as we did for 2 to the x, just replace all of the 2's with 3's, do the same thing, and you would get a limit of about 1.098 there. We could do the same for 4 to the x, replace all the 2's with 4's, and we would end up with this. And you could do the same for 5, 6, whatever numbers you like. None of these constants looks very nice to me. 0.693, 1.098, 1.386, very ugly constants. Mathematicians like really nice, pretty looking constants. What would be a really clean constant to get out here? Is there one particular number that would give us a really nice, clean answer? So if you are a curious mathematician looking for that, this is what you are led to wonder. For what value of b will we take the derivative of b to the x and get b to the x, just like we did here, 2 to the x, 2 to the x, times some constant, 3 to the x has got a 3 to the x, derivative of 4 to the x has got a 4 to the x. But instead of these ugly constants, we get the nice, cleanest constant that there is, the constant of 1. So what number b do you think might make that happen? So you'll notice that when b is 2, we get the constant that's somewhat less than 1. When b is 3, we get a constant that's a little bit more than 1. So you might be formulating some hypothesis in your mind right now about what this special b would be. And we're going to try to find it. We have an applet for you to explore this numerically, or graphically, rather, in a minute. But first, let's do a little bit more algebra here. So we're going to go through the same steps as we did with 2 to the x. Taking the derivative of b to the x, we get f of x plus h minus f of x over h. And then we do the same exponent rule as we did with 2 to the x. And then again, from the point of view of this limit h goes to 0, these b to the x terms are both constants. So we can pull them all the way out front, just like we did with 2 to the x. B to the h minus 1 over h. And this is the thing that we would like, this limit we would like to equal 1. So that's our question. For what value of b will this limit work out to be exactly 1? Because I hope you would agree with me that will give us a very nice, clean, good-looking answer. And we will have found a function, an exponential function, that is its own derivative, right? Because that will say that the derivative of b to the x is b to the x times 1, meaning the derivative of b to the x is itself. And so we have an applet for you to explore this numerically, that is to say by varying values of b. We hope that you will be able to make a good guess about what the value of b is that will make this happen. And we also have a graphical look. So we have an applet where we draw the graph of b to the x and its derivative, and we let you vary b to try to match them up. So you're trying to match up the graphs so that the derivative of b to the x is exactly the same as the b to the x graph itself. So this is, again, in keeping with our motif of looking at things in as many different ways as we can. We've got it analytically here. The applet, one applet is going to do it graphically, and the other applet is going to do it numerically. So please go ahead and play with those applets, and we'll come back and see if you have found the right value of b.